So let's get started then. So, well, today it's our pleasure to have Tom Hartman in Rencontres. And well, he will be talking us about replica wormholes and the black hole information paradox. So, stage is yours.
Okay, thanks very much for the invitation, chance to give this talk. So, the motivation for this, so I'm going to be describing a series of papers over the last year or so, some of them by other people, some of them that I'm involved with, but I just want to basically summarize the current status of this work. It's motivated by the page curve. So, of course, the page curve is the entropy of Hawking radiation, and what I've drawn here is the my pointer. So we have the Penrose diagram for an evaporating black hole, and we are collecting Hawking radiation in a region R for radiation up on Scry+. The Hawking radiation is coming out of the black hole, and it has some entangled partners in the interior of the black hole. And then we're going to plot the fine-grained entropy of the radiation. So famously, this just goes up, and this just goes up. So as in Hawking's calculation, this just goes up forever. And when the black hole is completely gone, it saturates at the thermal entropy of the radiation because you have this thermal radiation coming out. And this is the fine-grained entropy. Fine-grained entropy is not supposed to increase under unitary evolution. So that's the paradox. What should happen, as described by Page, is that at some point, well, one way to think about this entropy is that it comes from the entanglement of the radiation with the black hole. And the black hole entropy, given by the area of the black hole, is decreasing with time. So the black hole curve starts out at the area and then goes down to 0. And if you have entropy in the radiation that's coming from entanglement of the radiation with the black hole interior, then it can't be any bigger than the entropy of the black hole. And so, as Page described, the true entropy in a unitary theory should increase along the Hawking calculation, and then turn over at the page, what's now called the page time, the page transition time, and go back down to 0. Now, we should be careful what we mean by the paradox here, because of course we don't know how to do any of these calculations exactly. What we're really calculating, we're doing these calculations in some low energy effective field theory. And when we say that the entropy of the radiation is thermal, what we really mean is that when we calculate this density matrix for the radiation, then it has the thermal leading term with gray body factors that I won't write. The thermal leading term calculated by Hawking. Then, of course, there are perturbative corrections to this, and possibly non-perturbative corrections, which are suppressed by e to the minus s, the entropy of the black hole. As I said, this entropy that we're calculating is a fine-grained entropy, or von Neumann entropy, sometimes called an entanglement entropy, although it doesn't really have to come from entanglement. And that entropy is a trace of rho log rho. And when you do that trace, so in this trace here, there are e to the s terms that contribute in that trace, because we're summing over the microstates. So they're e to the s terms. So we have to be very careful about whether we can trust this calculation. We have these non-perturbative corrections that we know very little about, suppressed by e to the minus s, but they're potentially e to the s of them. And it's very easy just at a mathematical level to see that if you allow me to take the density matrix that we know from Hawking's calculation, if you allow me to just do whatever I want at order e to the minus s, it's very easy to change the entropy and make the calculation unitary, just by tweaking the off-diagonal terms by these small non-perturbative terms. Okay, so what do we really mean when we say there's a paradox? Well, it's only a paradox if you do a calculation that you trust and you get an answer that contradicts the unitary. It's not a paradox if you just can't calculate it. I think there are three good reasons to call this a real paradox. The first is that local corrections, local or small or perturbative corrections to quantum field theory and curved spacetime do not help. I think this was known for a long time, but really proved and sort of codified by entanglement arguments of Mator and coming out of the firewall discussion a few years ago. So the perturbative corrections here, we can just ignore those. Those aren't going to help us understand the entropy of the radiation. The second part of the actual paradox is that there's no mechanism known to calculate or to modify rho. So if there's going to be some fix, it has to show up in the non-perturbative terms, but it's not very satisfying to just say, well, there could be some non-perturbative contributions that we don't understand. We're going to need some kind of mechanism to understand what they are and to see that they actually give something unitary. The third thing that I think is a real paradox, and this is what I'm going to focus on in the talk. Number three is that you can actually directly calculate the von Neumann entropy in the low energy theory. If you calculate the density matrix, then you should worry about these e to the minus s contributions adding up with e to the s terms. But if you calculate the von Neumann entropy directly, if you have a low energy calculation that calculates SR, and you believe that you're using the low energy theory within its regime of validity, then that's certainly a paradox. And SR has been calculated directly in the low energy theory in a lot of these old references. So this is the aspect that, number three, is the aspect that has been understood much better in the last year or so. And so this is the thing I'm going to focus on. Basically, the summary is that we now understand how to calculate the radiation entropy in the low energy theory. And when you do this calculation, including the contributions that I'll describe in this talk, then the result that you get is consistent with unitary. I want to emphasize right from the start that this does not directly address number two on the list, because we're going to jump straight to the entropy. I'm not going to talk about calculation. I'm not going to talk about calculating the density matrix. And in particular, for example, I'm not going to give you a way of understanding how a particular incoming state, say a collapsing star, gets mapped to a particular outgoing state. And that's really an aspect of the paradox as well. So that is not going to be addressed by this. And also there's going to be some other questions that are raised by this calculation that I'll come back to as we go. So this calculation of the radiation entropy in the low energy theory is really an application of a more general result that's been understood in the last 15 years that I'm going to call a gravitational entropy formula. So the formula is written here. You may know this as the Ryu-Takanagi formula, and that's where it was originally introduced, was by Ryu and Takanagi. They introduced this formula as a formula for holographic entanglement entropy in anti-de Sitter spacetime. But I think part of what we've learned recently is that this formula is much more general than holographic entanglement entropy in ADS CFT. In fact, this formula does not require holography. It's more general than that. I'm not going to be assuming holography in this talk. The formula is not really a formula necessarily for entanglement entropy. It's just a formula for von Neumann entropy, which can have both entanglement contributions and other kinds of contributions. And finally, it doesn't require anti-de Sitter space. And although I will use ADS at points in this talk as sort of a crutch in order to be able to do calculations, I don't think that the conclusions rely on having an ADS anywhere. So I think this is really a formula for the von Neumann entropy of systems coupled to gravity. And it was understood to some extent earlier that this formula goes beyond holographic entanglement entropy, but didn't really have an application. And it's this application of Hawking radiation where this really became clear. By the way, I meant to say at the beginning that I encourage people to jump in as we go. So just interrupt and stop me if you have questions. Are there any questions at this point?
Yeah, sorry, Tom. So the way that I'm supposed to be interpreting this formula from the bulk point of view is that I have some surface sigma x, and this is supposed to give me the von Neumann entropy of quantum fields on this sigma x, and there's some gravitational contribution to it coming in this area term, coming from regulating something. How am I supposed to interpret it from the bulk point of view?
Let me postpone that because I'm going to be using this formula and I'll explain it better there. But yes, this is
what's the Hilbert space interpretation of this, and how am I supposed to understand the area? I guess the second term is clear. If this is supposed to be the von Neumann entropy of quantum fields on sigma x. Good.
This is a good point. Is that this formula, although this is a formula that you can derive. The statement that this has the idea that this has a Hilbert space interpretation is unproven. That's a conjecture about the microscopics. And so I would say that this formula is on a similar footing to the Bekenstein-Hawking formula for the entropy of a black hole. You can calculate it in the low energy theory. You calculate it by the methods that you expect to give an entropy, like taking 1 minus beta d beta of log z, the partition function, but that calculation doesn't really know about the microstates, and you have to do something much more detailed in the ultraviolet to find those microstates. So
yeah, sorry. So because this formula is only valid at large n, right? So I have some idea of what the Hilbert space is at large n, and this S semi-classical is presumably just the usual entropy of quantum fields on the spatial size.
This formula doesn't require large n.
Oh, it doesn't.
I'm not sure what you mean by large n. There's no holography here, so I'm not sure what even n is.
Sorry, small g Newton.
Yes, it's only true at small g Newton. That's right. This is I would describe this as a as a formula in the low energy effective field theory. The idea that there's actually a density matrix. So we're gonna derive this by calculating trace of rho log rho, but just like the Bekenstein-Hawking entropy, it's sort of a thermodynamic calculation. It's not actually accessing the microstates.
Okay, thanks.
Just for clarity, are we Euclidean or is this Lorentzian?
The formula is Lorentzian. The derivation will be a mix of Euclidean and Lorentzian.
Sorry, Tom, a clarification question again. So this is effective field theory, which contains gravity and some quantum field theory. What is the definition of effective field theory here?
Yeah, by effective field theory, I mean low energy gravity plus quantum field theory. I mean, we're not doing string theory.
Okay.
And one quick question. You said the von Neumann entropy can have entanglement entropy contributions and other contributions. Could you clarify what other contributions could be?
Well, for example, if you're in a thermal state, then the von Neumann entropy is the thermal entropy.
wouldn't you say that's entanglement with the thermal bath or something like that?
Well, it's true that any mixed state can always be purified if you want, but you don't have to think of it that way. Okay, so the goal in this talk will be to to understand the origin of this formula and its application to Hawking radiation, and in particular to derive the unitary page curve directly from a replica calculation. The replica method is a way of calculating that log and the von Neumann entropy. So logs are hard to calculate, especially with a path integral. On the replica method, we instead calculate trace rho to the n, and then analytically continue n to 1 to get the entropy. A very rough sketch of the idea, and this is what I'm going to explain as we go, is that when you have multiple copies of the space-time, so that, say we're calculating trace of rho cubed, then you're going to have multiple copies of the space-time involved in that calculation. And very roughly, what's going to happen is that in the standard calculation of the entropy, you just do quantum field theory in a fixed curve space-time. It's the curve space-time corresponding to an evaporating black hole. But what I mean is that the saddle point in the usual calculation of the entropy, the saddle point corresponding to 3 copies of the system is just 3 copies of the original saddle point. The main point will be that there's an additional saddle point where these wormholes open up in the black hole interior, and you get these bridges connecting the interiors of the multiple copies of the black hole. So this is a new saddle point that occurs when you consider replicas. And we're going to use these replicas to calculate the partition function. Then we're going to take n to 1. When you take n to 1, the wormhole, so these are complexified saddles, which are like space-time wormholes. When you take n to 1, the wormhole will be gone. There's nothing, when you have n equals 1, there's no wormhole because it has to join multiple copies of the system. So there's no wormhole left when you take n to 1. However, this leaves an imprint on the density matrix. The fact that you can have these wormholes does leave an imprint on the density matrix, and we're going to use the partition function to calculate the entropy and find this modified formula for the entropy that has a unitary page curve.
So are you?
Although the idea,
are you saying that you can actually you're using a gravitational path integral here, or you know, because that's notoriously poorly defined in the Lorentzian space, and or what is? So is this a quantum theory of gravity, or is this just gravity as a classical background, or what's the status here? Because I don't believe anything that involves just pure Euclidean path integrals or Lorentzian path integrals in gravity.
I don't think you have to believe anything more than what you believe to get the Gibbons-Hawking derivation of the black hole entropy.
Okay, so then you are Euclidean.
So yeah, the calculation is essentially done in Euclidean and then analytically continued. I guess you have to believe a little bit more than Gibbons-Hawking because you have to believe that that analytic continuation makes sense. That'll be an assumption.
Yeah, it's just the quantum gravity with purely Einstein action in 4 dimensions is a bloody nightmare. And so you asked me to buy some of the cow, but not all of it.
Yeah, I agree with that. But I think that's a similar. I think we can make a similar objection to the Bekenstein-Hawking entropy.
Well, I think the calculation involving Euclideanized action is a cool factoid that was known for 40 years ago, but nobody ever made a viable run of any other form of Lorentzian or Euclidean quantum gravity in 4 dimensions. So it's kind of a neat little observation, but I don't think it stands as something. That,
what are you referring to as a neat little observation?
Well, the fact that you can Euclideanize the action and calculate the partition function and get the Bekenstein-Hawking entropy from the Euclidean path integral as a saddle point.
I think it's more than a neat little observation. I think it's a approximate calculation of the gravitational path integral, and that Euclidean gravity is.
Well, wait a minute. Then, if you're going to say I'm going to do the whole Euclidean path integral, what are you going to do about regularizing the conformal factors, which are unbounded below?
So we certainly don't want to do the whole path integral, and since we're not claiming that Einstein gravity is UV complete or has a well-defined path integral, we don't want to do that. In principle, we want to do the path integral in the UV theory, but we don't have the UV theory. We're going to make the assumption that we can approximate it by a saddle point in the low energy theory. I agree that that's not obvious in gravity. The relationship between Euclidean, I think in quantum field theory, this would be totally standard and nobody could complain.
Absolutely, but that's always the problem with quantum gravity.
Yes,
everything that's absolutely standard in quantum field theory doesn't work.
I take your point. I think that the relationship between Lorentzian path integrals in gravity and Euclidean path integrals is not nearly as well understood. I don't have anything to add to that, really. I'm going to be using the Euclidean path integral to derive this. If it's really just an assumption that we're allowed to use Euclidean gravity. I think this is a reasonable assumption, but I don't think that. I think that there could be input from the ultraviolet, for example, how to define the contour in the space of metrics, and we don't know how to directly go from there to the Euclidean path integral in the infrared. I agree.
Tom, I have also a related question. Typically, when you have wormholes and you go to Euclidean space, they split off. What happens here? They get disconnected.
This is a space-time wormhole. So I think, I'm not sure what you mean. They're split off in Euclidean or in Lorentzian?
No, precisely. If there are wormholes in Lorentzian and you go to Euclidean, typically because they have horizons, typically when you go to Lorentzian to Euclidean, they become disconnected.
I see. Okay, so this is a space-time wormhole, and it's really best understood in Euclidean. The picture that I just drew is meant to be only motivational. I'll describe these wormholes in detail a little later.
Okay, thanks.
Although I think a lot of the things that I'm discussing here are general, the details have been worked out only for some simple models in 2 dimensions. In particular, the wormholes that I'll talk about can be constructed in a local sense. They can be constructed in general. I can explain what I mean by that later if somebody asks me. But the complete derivation of the wormhole as full global solutions of the equation of motion has only been done in a couple of examples in 2-dimensional dilaton gravity, including the one that I'll talk about. So at this point, I'm going to specialize to this model where we really know how to do all this in great detail.
Sorry, Tom, just one more question about the generalized entropy formula. I just got a bit confused. So what is fixed in that formula? So when I have a holographic interpretation, what I'm fixing is the boundary region.
I'll come back to, I'll answer that in a minute. I'm about to use the formula.
Thanks.
Okay, so the model was introduced in this paper here. Has ADS2 black hole. In the ADS2 region, you have JT gravity plus a large n coupled to a large n matter sector, which is conformal. And what the insight that they had in this paper was that, so if you just have an ADS black hole, it doesn't evaporate. The Hawking radiation just bounces back. The insight that they had in this paper is that you can make evaporating black holes in ADS in this model where you couple it to flat space. So this is on the exterior region. This is a flat region with no gravity. G Newton is equal to 0, but it still has the large N CFT. So in other words, there's radiation coming off this black hole, which is able to escape into the flat region, this black hole is now asymptotically flat, but it's in this sort of strange hybrid theory where you have an ADS2 region with dynamical gravity and a flat region that does not have dynamical gravity. Now, I'm going to discuss a variant of this calculation that they did that's more convenient for the Euclidean calculations that I want to describe. But I want to make a black hole. We want to form a black hole. Okay, so we want to form a black hole and then let it evaporate. And the way that we're going to do that is by sending in a shock wave. Okay, so we're sending in a shock wave from the flat space region. Then we're letting the black hole evaporate, and then we're going to collect the Hawking radiation and calculate the entropy. For Euclidean purposes, this is what the black hole looks like. So the geometry is the usual cigar geometry of the Euclidean black hole. Let's see. The left of this diagram is, so this left part of the diagram is the JT gravity and ADS2 piece of the diagram. The right part of the diagram is flat space-time.
Sorry, Tom. So did you have a two-sided black hole or a single-sided black hole?
I'm only going to draw the right side because I only need that one, but there's really also a wing on that. There's a thing, you're asking about this thing? That's there too. I'm just not going to draw it.
I see. So the way that, I mean, because your Penrose diagram looks a bit like an eternal black hole.
Yeah, yeah.
So was the black hole pre-existing and you're sending in the shocks to make it, or?
It's convenient.
Was it pre-existing or you're making it by the shocks?
Yeah, so it's convenient to make it to start with a pre-existing black hole, but we're going to take the shockwave to have much bigger energy than the pre-existing black hole.
Mm-hmm.
The fact that it's pre-existing is just convenience for doing the calculation on a circle instead of on a line. The black hole that we're making has much bigger entropy, so you still get all the usual features of the information paradox and page curve and so on.
I see. And where can I see the evaporation on your Penrose diagram?
That's these wiggles coming out.
I see. So sorry. So I'm starting with the pre-existing small black hole. I'm saying being in a shock or two shocks to make it bigger. And then it doesn't evaporate. Does it evaporate completely or no?
Yeah, that's right. So if we had not sent in the shock, the horizon would have been somewhere else. The horizon would have been up here.
Mm-hmm.
But by sending in the shock, we've brought forward the horizon and it evaporates. In ADS2, it basically just, I mean, so in ADS2, the black hole doesn't really have a singularity. It just, so,
Right.
Yeah. Okay, so here's the Euclidean picture.
You're saying that sorry, am I supposed to understand that the way that I'm seeing that it's really evaporating, but not completely, is that somehow the coordinate patch that's finally covered by the geometry is?
It's smaller than it would have been.
It's smaller than it would have been for the largest size of the black hole.
It's smaller than, let's see, a bigger black hole has a smaller, covers a smaller coordinate patch.
Uh-huh.
So the fact that it evaporates allows it to cover a little bit more.
I see. And does it cover as much as it would have covered without the shock?
No, it does not. So in particular, the fact that the fact that this diamond does not go all the way across is accurate. Even as we take the temperature of even as we take the initial black hole to have 0 mass. Okay, so to make the shock wave, we insert some operators in the CFT. So these operators, so in effect, we're thinking about the CFT state. If we were just doing CFT, this would be like the state with psi of I delta acting on the CFT vacuum. However, we're doing this on top of a Euclidean black hole. This operator insertion in Lorentzian is going to produce a shock wave that falls into the black hole, makes it bigger, and then allows it to evaporate.
Stupid question, the CFT is a 0% dimensional CFT due to ADS2 or some other CFT?
No, this is just a two-dimensional, this is the two-dimensional, so there's no duality going on here. This is the two-dimensional matter theory that's coupled to JT gravity.
Mm-hmm. Okay.
Could be n free fields.
Okay.
I'm taking n large because I'm going to need to, well, first of all, I don't want to deal with graviton fluctuations because we don't really know how. And second of all, it's easier to talk about these saddle points when I can stabilize the quantum fluctuations with large n, although I don't think that that's actually necessary.
So just a theory coupled is like in Randall Sundrum, for example, when you just take an ADS CFT and you just stick in some brain on it, there's a theory living there, and that's the theory you consider. It's
yes.
Not, okay.
Yes, it's like that. Yeah.
Okay.
And
is it a CFT or is it just some random? Why does it need to be a CFT? Just stupid question.
It needs to be a CFT just so we can calculate things easier.
Oh, calculating. Okay. There's nothing fundamental. There's no fundamental reason because in Randall Sundrum, for example, you don't need to have a CFT on the brains. You can have a CFT if you want, but it's up to you.
Yeah, there's no fundamental reason. It's easier to calculate the entanglement entropy when it's a CFT.
Okay, sounds good. Thanks.
Sorry, Tom, you mentioned graviton fluctuations. There are no propagating gravitons in 2 dimensions. What do you mean?
Well, there's a boundary graviton, which is the Schwarzian mode, and I don't want to have to worry about that. The quantum, I don't want to have to worry about the
I see.
one loop Schwarzian. Okay, so this is this makes our state. Now I want to describe this gravitational entropy formula and how it was used in these papers of Pennington and Almeri, Engelhardt, Marloff, and Maxfield to calculate the entropy of an evaporating black hole. So here's our setup again. We have our shock wave making this black hole in ADS2. And we want to calculate the entropy of the radiation in region R. So we're collecting the Hawking radiation in region R, and we can view region R as a function of time just by pushing up by pushing it up along the Penrose diagram, and we want to calculate its von Neumann entropy. So the formula that they proposed, which is a generalization of the previous fine-grained entropy formula, but I think really all fits into the same framework, is the formula written here. So let me go through this in some detail. First of all, the point is that at late times, a region called the island appears inside the black hole. Okay, so what happens all the way on the left of this diagram won't be important, so I'm not going to worry about it. The island is a region inside the black hole that includes the interior partners of the Hawking radiation. So like at late times, there's all this Hawking radiation that has been collected in region R, and there are interior partners of that Hawking radiation that live in region I. I should really be drawing that after, I should really be drawing that radiation as coming after the shock wave, but it doesn't quite fit on my diagram. Okay, so there's radiation in R and in I, and the radiation in I purifies the radiation, the quantum fields in R. So the claim of these papers is that we should find the island dynamically, and we should find it by this formula, which says that we take the generalized entropy, the thing in brackets here is the generalized entropy, of the union of the radiation with the island, and then we should extremise over the choice of the island. The final minimum in this formula is telling us that if there are multiple extrema, we should take the extremum with the minimal entropy.
Okay, Tom.
Tom, in the context in which this formula was first considered, the second term was considered to be a perturbative correction, that is of order G Newton to the 0. And in the application that you're about to describe, you're treating them kind of on the same footing. So in some sense, all the magic is going to happen because these two terms compete with one another. Could you comment on the validity of that, extending this formula to that regime?
Yeah, sure. So I am going to make this assumption that we have large N matter. And when you have large N matter, these two terms really are on the same footing. This is a similar trick that was used in the early 90s in dilettante gravity. If we have large N matter, then we can take a limit where the one loop matter term and the area term are the same size.
In the early 90s, that didn't end well.
Fair enough. It's going to turn out better this time. And I'll come back and compare. So that's, for the purpose of this talk, that's my answer. Now, I don't think that's actually required. And the reason for that is that even if we have small n matter, at late times, these two terms do compete with each other because there's the kinematics of T. So at late times, these two terms do compete. And I think that although we don't know exactly how to calculate we don't know exactly how to do the calculation at small n, they do compete, and I do expect that a lot of these things will carry over. But let me leave it at that and just assume a large N for the purposes of this talk.
Can I ask,
thanks.
That whether it sort of looks like you're almost putting in what you're trying to prove at the end of the day. I mean, by postulating there's an island that purifies or largely purifies the late outgoing radiation.
Absolutely.
We kind of knew that. So it's like you're pulling out a rabbit out of the hat, having stuffed the rabbit conspicuously into the hat at the beginning.
Very good. So I think that the first papers on this had that kind of flavor, pulling the rabbit out of the hat. But the purpose of this work and this talk is to derive this formula directly from a replica calculation. So if this formula was just a postulate, then I agree. But we're just going to derive it from the gravitational path integral. So that's why I think this is a derivation, we're not putting in the answer. It's the gravitational path integral that's telling us that this formula is correct.
But it's the Euclidean path integral you're going to derive it from, or the
Euclidean.
So the Euclidean cuts off the space at the horizon, so it doesn't know anything about I.
The Euclidean calculation analytically continue. So we're going to do a calculation Euclidean, and we're going to analytically continue the endpoint of the region R, and that's where we find that you do know about I.
Okay.
In other words, when I say Euclidean path integral, I really am referring to an Schwinger-Keldysh type path integral. I'm really not doing a purely Euclidean path integral. I'm using the Euclidean path integral to prepare a state, but then we're going to go into Lorentzian and also use the Lorentzian piece of the manifold. It's an in path integral.
So your saddle points are complex.
Yes.
Sorry, Tom, can I come back to my question about how you define this region R actually at the level of the first time you wrote this formula? So if your theory, so I'm guessing that here the Minkowski part of the geometry is actually not coupled to gravity, so it makes sense to define the spatial region R, and you can define your density matrix on it.
Right.
But then if I have a fully quantum gravity theory, how do I define the whatever you're calling sigma X in the previous formula?
Yeah, so say we were doing black holes in asymptotically flat space, then I think the comment that you're making is that this is now a region in a theory of gravity, and we shouldn't really be able to talk about that region. So I think it's safe to talk about that. I think if G Newton is finite on the outside, I think it's safe to talk about that region when it's on Scri plus, because I do think we can talk about regions on Scri plus, even
because
when there's
gravity is weak there somehow.
Yeah, yeah. However, I would say that this needs to be understood better. I mean, I find, you know, this gluing of ADS to flat space is not ideal. We'd like to understand how to define that region better, but I don't think it's fully understood.
I'm still not understanding whether if you want to interpret this generalized entropy as trace rho log rho of some rho defined on some spatial slice, I'm still not understanding how you're defining the spatial slice in a theory of quantum gravity. But maybe it's just...
Well, I mean, region R is region R is just matter. There's no gravity there, so there's no point.
Yeah, exactly, because you're taking, so in this particular example, indeed, you don't have to deal with it because the Minkowski region is not coupled to gravity. But the general formula that you wrote before, in principle, is coupled to gravity. And then I'm a bit confused.
I think that general formula makes sense when the region is on the boundary of ADS. It makes sense when the region is in some non-dynamical flat space like this one. I think it also makes sense on Scri plus.
I see. So, but I cannot take a region that passes through a black hole horizon or something.
No, I don't think so.
Okay, great. Okay, so the understanding is limited, but okay, good. Thanks.
Can I ask a question that goes back to Emil's question? If you're saying that in these the two terms competing in this entropy formula become of the same order, shouldn't you worry that also higher order terms become of the same order?
Yes, but that's not going to cause a problem. Basically, because we'll include all the terms that we know. If there are more terms, this will make more sense in a few minutes. But if there are more saddle points that we don't know about, then they'll only make the page curve they'll only make the entropy smaller, and therefore won't cause a problem with the unitary.
Okay, thanks.
Okay, so we're going to derive this formula by the replica method. The derivation is very similar to earlier derivations of the generalized Rutai-Kannagi formula, but instead of applying this method to the asymptotic ADS boundary, we're going to apply it to the radiation in the flat space region. Now we get to the replica calculation, which is the main thing I want to talk about. I only have 10 or so minutes to talk about it, but that should be plenty. Okay, so we want to calculate trace rho to the n. I'm going to describe this calculation in Euclidean, but as I said before, it's really a Schwinger-Kaldich type calculation with a complex saddle. The density matrix of the Euclidean, the density matrix for region R is calculated in Euclidean by the path integral that I drew on the top here. So what does this mean? Well, we're calculating the density matrix, so its matrix elements are given by specifying the data on the top and bottom of region R in Euclidean signature. So you think of this as the bra and cat. Now we want to calculate trace rho R to the n. for n equals 1, let's start with an easy case, which is n equals 1. For n equals 1, taking the trace just says that we should take I equal to j and sum over it. Okay, so this is sum over I of this cigar geometry with I on top and bottom of the cut. Well, when you do that sum, that's just inserting the identity there. So we can just delete the cut entirely, and we're just doing the path integral on the cigar. This is just the usual calculation of the free energy of the black hole, given by the gravitational action and the one loop contribution of the matter fields.
And the cut is terminating on the horizon, or where?
The cut is region R. So if we go back up, it's the radiation region. So the cut is terminating at this at the edge of region R here, which you can take to be at the boundary of, you can take to be at this region at the point where you glue ADS to flat space, or you can take it somewhere further out in the flat space.
Okay, thanks.
This dashed line, the dashed lines here were meant to indicate the place where you glue. So you have gravity over on the left and no gravity over on the right. Okay, so now let's go to n equals 2. If we want to calculate trace of rho r squared, then we're supposed to do a path integral with the appropriate boundary conditions for the product of two copies of the density matrix. Now, a crucial point here is that when you do gravitational path integrals, you don't specify the geometry. You specify the boundary conditions. And it's up to gravity and the equations of motion to find the geometry that has the appropriate boundary condition. So when I say it's a path integral, a gravitational path integral, we're really just specifying the part that I drew here. And then it's up to the equations of motion of the theory to fill in the dot, dot, dots. Of course, we don't know how to do the path integral in detail, but we're going to assume that we can approximate it by a sum over saddle points, and then just draw all the saddle points that we know of with these asymptotics. So there's one obvious one, which I'm going to draw. Since you have two copies of the black hole, you can just draw two copies. Okay, so there were these cuts. So these are two copies of the black hole that are glued together on the cuts. So this is what we would normally do to calculate entropy in curved space. So I'm going to call this the Hawking saddle. In particular, if you can very easily generalize this to all n, and if you use the replica trick and continue n to 1, you're just going to get the usual Hawking answer for the von Neumann entropy of the radiation. However, now that I've drawn it this way, it's clear what I'm about to do. There's other saddle points that we should worry about and include in the path integral. So here's one of them. This geometry is glued together on the cuts, but it's also joined through the black hole interiors. So this is the kind of Euclidean geometry that we call the replica wormhole. It's a higher topology contribution to the Euclidean or Schwinger-Keldysh path integral, and we should ask how it contributes to the entropy. Now there could be higher terms. For example, we could draw something like this with a hole and plus dot, dot, dot.
Sorry, why do you say it's in the interior of the black hole? Because the horizon is at the tip of the cigar, right? So if you join this way, it looks like it's outside the horizon.
Well, by inside, I mean inside. Yeah. if you do this if you really do this in Euclidean, of course, the black hole doesn't have an inside, but I would say they're sort of glued together at the Euclidean horizon. When you go to Lorentzian, when you analytically continue this to Schwinger-Keldysh, the black hole does have an inside, and this gluing is taking place in the interior. In fact, it's taking place essentially at the island that I described a few minutes ago.
So you have your Minkowski solution associated to this that has the property that you can see the wormhole inside.
Yes. Yeah. So when you calculate trace of rho squared, it has contributions from the different saddles. The contribution from the Hawking saddle, I've called e to the minus S2 Hawking. I'm calling it S2 because, so this trace of rho squared is called the purity in quantum information. S2 is the second Rennie entropy for this associated to this saddle. So this is a different measure of entanglement. It's similar to entanglement entropy, just a slightly different measure of entanglement. But the point is that there's a contribution from the Hawking saddle and there's a contribution from the wormhole. And let's compare these. Now, the wormhole saddle has an extra. So S2 wormhole comes from this higher topology, contribution, and JT gravity has a coupling constant that suppresses things by the topology. So there's a parameter, there's a large parameter S0 in JT gravity, and when you have higher topology, things are suppressed by S0. So the wormhole contribution is very small because it's higher topology. That's the point I wanted to make. However, and you might think therefore it never contributes. But this Hawking contribution is very small at late times. So this is small when entanglement is large, that is entanglement between the interior of the black hole and the radiation. So that's exactly the kind of situation where you run into paradoxes. And what can happen, and what does happen in this example, is that the Hawking saddle dominates at early times, but as you time evolve this, eventually the wormhole saddle takes over and is going to give us the unitary page curve. Log trace rho squared is just the minimum of these two contributions. I should have put a minus sign on there. At late times, as I said, S2 Hawking is very large and S2 wormhole dominates the path integral. Generally, this S2 Hawking becomes large when the semi-classical Hawking radiation is highly entangled with the black hole interior, which is exactly when you run into paradoxes. So that's really the gist of it. I'm going to just briefly describe the higher replicas. So here's a picture of an n=3 replica wormhole. You now have 3 copies of the asymptotic region glued together. If you really wanted to consider all possible geometries like this at higher n, things would become awfully complicated. We can simplify things by assuming that the saddle points are Zn symmetric. So in this case, there's a Z3 symmetry that just rotates the 3 copies of the system. So I'm going to assume replica symmetry. And if you assume replica symmetry, then you can view this manifold, you can take a Zn quotient, and you can view this manifold as a branched cover of a single copy of the black hole. So what's happened on the right here is that we have a new branch cut appearing near the black hole horizon. Once you've taken this quotient, the equations of motion make sense for non-integer n. In the replica trick, we need to be able to analytically continue in n. So if we assume replica symmetry, then we can do this continuation by taking the quotient. then we continue n to 1 and solve the equations of motion to find the saddles. This we've done explicitly in this example and some related examples. So this is actually a saddle which you can find and you can solve. The equations of motion so finding the equation of motion actually turns out to be pretty difficult because the equations of motion for this are non-local. The equations of motion involve the one loop contribution of the matter fields on this crazy manifold, so that's a non-local contribution to the stress energy, and then you have to back react that non-local contribution. You have to back react and consistently solve for the gravitational part versus the matter one loop contribution. But that can be done explicitly using some techniques that were developed in ADS2 gravity, where you replace this by a Schwarzian theory living at the boundary, and then you solve the Schwarzian equation of motion, which I won't go into. So let me sorry, go ahead.
Is it possible to explain in a simple way how you determine the endpoint of this new branch cut, or one just has to look at the equations of motion?
For finite n, so say n is 3 or something, the answer is that you just have to solve the equations of motion, and I don't have it's hard. It's hard. As n goes to 1, things become much simpler. So here's the sketch of the calculation, and this is now basically following what was done by Dye and Lefkowitz in asymptotically ADS. For n near 1, what happens is that the new branch cut just acts like a defect, and you can calculate the effective action for that defect. And what you find is that the effective action for the defect is the area term in the entropy. Now you also have a contribution from the matter fields, which give you a matter entanglement entropy. So the total effective action of the defect is, in fact, the generalized entropy of, not of the original region, however, and that's sort of the surprise of the island. It's the generalized entropy of this situation where now you have this new branch cut, this new dynamical branch cut coming out of the solution of the equations. So if the effective action is the generalized entropy, then it's not so hard to see that the entropy you get from that is going to be the extremized generalized entropy, and that is the island rule. Is there a question?
I was just again asking, is this Euclidean or Lorentzian? You seem to be making a sleight of hand to move us back to the Lorentzian regime because you're talking about islands again.
Yeah, it's Schwinger-Keldysh. It's a path integral that goes for a semi-infinite range in Euclidean, then goes up in Lorentzian, then turns around and comes back down, and then goes the other side in Euclidean.
And sorry, Tom, to see that the island is behind the horizon, is there a simple way to see it, or one has to stare at the equation?
There's no simple way I know of to see it. There are other situations where the island can be outside, and I don't have a good sense of how to see that. Yeah.
Maybe I ask a heretical question, but you know, if you started right from the beginning, you said, okay, I've got this radiation field that's got a lot of entropy in it. It's entangled with a whole pile of states inside. The island is essentially saying, isn't it just simply saying, here's where we may have to localize this bunch of states that purify the radiation at infinity. So I'm trying to see whether this is just a cute geometric reformulation of something we already knew. And the thing that we already knew is that inside the black hole, there's a lot of states that purify the radiation. And you're just simply saying, here's perhaps a geometric realization of those states.
Well, I guess if we assume things are unitary, then we already knew this. I think what we did not know is that the low energy theory secretly knows this. I think that's the surprise. I don't think, I agree, it's not a surprise that that in a unitary theory, of course the radiation must be purified by the interior. I think the surprise is that you can calculate this in the low energy theory.
Tom, I think the non-trivial thing here is that these precisely are encoded in the geometry.
Right, right, yeah.
No, I don't have issue with the statement that, you know, we know there are states inside the black hole that purify the radiation. And I think it's perhaps kind of neat that you can find this geometric realization of those states. But as an explanation of what's going on with the black hole, it's no further forward. It's just acute geometric realization of that statement that there are states inside that purify the radiation. Just like the original Gibbons-Hawking calculation of the gravitational action and the Euclideanized black hole is a neat way of getting at the entropy. It's kind of nice, and it's a geometric route, but it doesn't explain anything about the radiation, you know, the information itself. You're just encoding it.
Maybe this is just sort of a matter of philosophy, but I do think that the Bekenstein-Hawking, I do think the Gibbons-Hawking calculation of the entropy is not, I don't think it's just a neat trick. I think it's how the entropy is encoded in the low energy theory. I think what you're saying is that unless you can solve problem 2 on my list, you haven't done anything. Problem 2 being find the density matrix whose entropy you're calculating.
Okay, so let's put it another way. Why wasn't, after Gibbons and Hawking calculation, that everybody said, well, the Hawking information paradox is solved? Because we know how to calculate it in terms of a microscopic theory. What this is just as an elaboration of that old story where you say, yes, I can find this neat geometric localization of the states that purify.
No, I disagree. I think the problem was that when you, in the previous method of calculating the radiation entropy, we thought we knew how to calculate its entropy in the low energy theory. And it was giving the wrong answer. Even after Gibbons-Hawking, it was still giving the wrong, I mean, that didn't tell us how to calculate the page curve or the entropy of the radiation. I agree, there's a more microscopic question that has certainly not been answered, which in the Gibbons-Hawking case is what are the microstates that are responsible for that entropy? That's in the Gibbons-Hawking case, that's a question that's not answered by Gibbons and Hawking. But it's a UV question, and I'm not sure that now maybe we're just talking about definitions, but I'm not sure we should count that as part of the paradox. Like the paradox is about a conflict between what you have a unitary theory and what you see at low energies. It's not just the fact that you don't know how to calculate things at high energies. It's about this conflict that you see at low energies. And I think that what the island formula gives you is it's the analog of Gibbons-Hawking, but for the entropy of the radiation, not for the black hole, the entropy of the radiation. If we were just using the Gibbons-Hawking formula to calculate the entropy of the black hole and saying, oh, look, it's the area which is decreasing, then that doesn't address the problem of the entropy of the radiation, which is the new thing.
But in some sense, the entropy of the radiation, we kind of know that it's got to be entangled with stuff inside the black hole. And if you can, so am I supposed to think of this as something fundamental that captures that information, or is it just simply that the stuff inside the black hole that purifies the radiation, and you can produce this neat geometric formulation for that stuff?
Yeah, even for the simple.
Try to answer the question. I mean, we knew it, but we didn't know how to show it. That was the problem.
Okay, maybe it's the word "show it." I mean, I think. Look, I'm not saying that. I'm not trying to minimize the neat thing that Gibbons-Hawking did. I'm not trying to minimize the fact that this is an interesting geometric realization of something new, which is the radiation. But in some sense, it's sort of saying, okay, we know that there's this stuff in the radiation, and we know it's entangled with stuff in the interior, and therefore let's try and make a geometric thing in the interior that somehow captures that.
Yeah, you could phrase it that way. Although, I mean, in the end, you don't try to make anything, you just solve the equations and they give you this formula. I mean, okay, we knew the answer before we knew how to derive it, but it's the low energy gravitational theory that's telling us to include this island region. That's the point.
It still bugs me that it's formulated in Euclidean path integral quantum gravity. Okay,
I completely agree that well, I don't know if I want to call it a defect of the derivation or the setup. I totally agree that what that means is that it's sort of a shortcut to the entropy that bypasses the very sticky question about how the density matrix evolves from early to late times. It bypasses that. I don't know. I guess the way I think about it is that the problem when you phrase it that way in terms of the evolution of the density matrix, then you really have to worry about these e to the s these e to the s terms with e to the minus s corrections. So I don't think it's very hard for me I don't know how to state a paradox in the language of the density matrix itself, because I don't know how to calculate those e to the minus s terms in the off diagonal pieces of the density matrix. So we can try to phrase it in a precise way that really gives a paradox by talking about the entropy directly. And that's what we've done. But then once you try to phrase it in that direct way in terms of a calculation of the entropy, then you find that Euclidean gravity is somehow smart enough to be able to get the right answer. I agree, it's still somewhat mysterious, but that's the picture.
I don't disagree with the statement. There's a miracle that somehow Euclidean quantum gravity is smart enough to find this answer, but.
Right. Okay. I'm out of time, so maybe I'm just going to sort of jump to the conclusions. I had a couple comments which I can make just in 1 minute. So one is that although I used ADS, similar results apply to black holes in flat space. The wormholes have not been completely derived in this case. They can be derived locally near the branch point, and they do give the correct equations of motion for the quantum extremal. I forgot to mention this island thing is called a quantum extremal surface. It gives the correct equations for that, but haven't been derived globally. The other comment was that, well, there's another piece of this, which is that it's suspected that based on general properties of the entropy and relative entropy in particular, it's expected that if you get the right entropy from the island rule, it also means that the radiation encodes region I. By encodes, I mean in the same sense in a sense that's very similar to ADS-CFT. So for example, if there's a field operator phi of x if you have some field operator phi of x in region I, then what this strongly suggests is that phi of x can be decoded as some very complicated operator on the radiation. And there's a proposal for how to do that in the Stanford paper using what's called the PETS map.
Sorry, doesn't that therefore make the point I was trying to make, which is that the island consists of basically some kind of semi-classical description of all the crap that's fallen into the black hole that will purify the radiation?
Yeah, I agree with that. I agree with that. That's exactly what it is. But yeah, I agree with that. The part of your comment that I was pushing back on was that we've somehow put it in by hand because we knew it was supposed to be the answer. But it's really the Euclidean path integral that told us we were supposed to do that.
You know, I think that's a sort of neat thing to say. But you know, in the sense, you know, if I was a betting man 5 years ago, I would say, look, there's a pile of crap inside the black hole that's going to purify the radiation, and maybe there's a semi-classical approximation in which it forms a structure. Okay, call that the island, and it purifies the radiation at infinity. We kind of knew there was something like that in there. The fact that Euclidean quantum gravity gives you some path integral that you know, has a saddle point associated with some structure. It's kind of neat.
Yeah. Okay, so let me end there. As I've been stressing, we've calculated the entropy, and this is only one part of the information puzzle. It's sort of this trick of going to Euclidean is somehow bypassing the details of really being able to describe how the density matrix evolves. We certainly can't calculate its matrix elements. I expect that you need a ultraviolet completion to do that, but maybe more can be said even in the low energy theory. So we don't know rho r. There's another thing I'll just mention, which is that there's problems with including Euclidean wormholes in the path integral. In particular, that there are other situations where if you include Euclidean wormholes, it just doesn't make sense. It doesn't really fully make sense as a quantum theory anymore. You get situations where, for example, two partition functions that should just be completely factorized from one another can be correlated. And there's been understanding by Sajsenker and Stanford in the two-dimensional context that this is related to ensemble averaging. So I think there's an open question of whether replica wormholes and the associated island rule are somehow know about this average or rely on this average or computing some kind of average for you, or whether they're something that you really include in an individual copy of the microscopic theory. And I'll stop there. Thank you.
Thanks, Tom. Yay.
Looks like Under vanished, so he was supposed to ask if there are questions. I think there's a question on the chat. How do you make sense of the wormhole saddle point contribution when n goes to 1? How do you know that it is a physical contribution and not an artifact of the replica trick?
Yeah, that's a great question. I think that anytime well, first of all, the continuation of n to 1, that is not a big deal, because when you take this, when you quotient, you can just solve the equations of motion for non-integer n. And that's what we did. The equations of motion make perfect sense at non-integer n, and you can solve them and calculate their action. The question of whether you should include this in the path integral, however, is an important question that we don't know the answer to. In general, if you just have a low energy theory, you don't know what saddles to include. That could be some input from the UV, and it could be that some saddle points you should include and some you shouldn't. We've just included them, and they gave the unitary answer, but we can't show from first principles that you're supposed to include these as approximations of the path integral. I think it's logically possible that there are some theories of gravity which are unitary in the UV, where the correct prescription is to include them, and other theories of gravity where maybe universes form or something and it's not unitary in the UV, and you're not supposed to include them. I think we can't answer that question from the low energy.
Can I ask a question?
Sure.
Usually, if I think of this in the context of holography, we do believe, if we take the orthodox view, that the black hole is some pure system which happens to be very complex and approximately looks thermal, because we understand now from many types of theorems that complex systems, even if they are in pure states, if you look at some things, they may look thermal. Now, this could, and therefore, we do not believe that, of course, there is some ensemble average in such a type of black hole, which is dual, let's say, to a pure state in a quantum field theory. But if you ask a question about appropriate, let's say, observables, it may happen that the answer is very close to thermal, and therefore it may look as an ensemble average. This is the way that I should understand your calculation, because as you said, there are other contexts in which an ensemble average doesn't make much sense in the context of gravitational path integrals.
Yeah, I agree with that. I think that this entropy is probably a self-averaging quantity. In other words, individual elements of the ensemble probably agree with the average. So in that case, I'm not sure there's even a clear difference between, I'm not sure you can even ask the question whether this is calculating the answer or the average.
For example, I mean, in the case, for example, of the theorems shown by Lloyd long time ago, he has some precise statements, which says that if you look at this particular context, what you're going to find is something close to the thermal ensemble, or if you look at this context, then it doesn't have to be thermal. Now, there should be something analogous here.
Yeah, I think maybe a way to do that, or to start doing that, would be to look at some related quantities where the non-averaged answer is 0. It's hard to tell the difference when it's hard to tell it's hard to address this if the average answer is the same as the non-average answer. But there are other situations where the average answer is non-zero and the individual answer is just 0. So an example would be if I go back to these wormholes and I delete the bridges coming from the original branch cut, well then these are just two completely disjoint quantum systems, and it doesn't make sense for them to have correlations, whereas they can have correlations in the ensemble. I think this is a little like I don't know about this. I don't know what the example was that Lloyd had in mind, but maybe this is something similar.
No, in fact, I know the things where he proved the theorems. I don't know of examples where at least one can implement in this context, but it might be interesting to think in that direction.
Okay, thank you. Yeah.
If I may ask also, for an analysis based on the Euclidean point of view, I have a problem with Gibbon soaking, which is like the procedure does not seem to work quite generally. Like if you do Schwarzschild black hole, there is this beautiful Euclidean solution which has exactly the right entropy. But if you try to do Kerr, already there is not a well-defined analytic continuation of the solution that gives the smooth instanton. And in general, it's not quite clear how to make correlation between an instanton and a Minkowski solution. For example, they are much more instanton in general because the Euclidean action has a much more solution that do not analytically continue to a real solution. So how don't you need to make something that would make sense for generic solution? Or
I think we have the same problem here. So we've bypassed that by this gluing of flat space to ADS2. I think that those problems come from well, like for example, if you really work in flat space with gravity everywhere, then you have infrared divergences from the matter entropy, from the matter radiation. Here you don't have that, which comes from turning off gravity in the outside. If you wanted to have,
it's more that I don't know an analytic continuation of the Kerr horizon that would be a smooth cap.
Oh, you're talking about the rotating black hole?
Yeah, for example, yes.
Well, if we take imaginary angular momentum, there's no problem forming a Euclidean rotating black hole, right?
No, that's right. But as far as I remember, unless I'm saying something wrong, there is no nice quantization of the circle that gives back the Hawking entropy when you do that, as opposed to the Schwarzschild solution.
I see. Okay, I misinterpreted your question. I think Gibbons-Hawking does work for. Are you worried about matter contributions or just the gravitational contribution? I think Gibbons-Hawking for the gravitational contribution, Gibbons-Hawking still works for the rotating black hole if we use imaginary angular momentum. I thought.
I thought not, but maybe I should cross-check that.
It was a long time ago, but I do remember that there were some situations where it didn't work so well. I can't remember what they were, but
at least there are strange situations where, for top nut, for example, you get a strange quantization between nut and mass that does not seem to make any sense from the Minkowski point of view, where you would like just to disregard any nut solution. But I saw that KR was a problem as well. But okay.
This is why I tend to think that Euclidean path integrals are just black magic.
Sorry, just a quick question about the, so in your talk, you took the region R to be space-like, I guess.
Well, that's right, yeah.
So what would happen? So I think there was some paper by Suvrat where he was taking the region R to be along the scribe plus. And I think you're finding some sort of flat page curve. Can you comment on what would happen in that case?
I can try. Yeah, let me put up my picture of flat space here. So the calculation that we did in flat space was for this region on scribe plus, in the limit where you push it all the way up to scribe plus. Now, this paper of Suvrat said that there is no page curve. Essentially, that the entropy at infinity is always zero.
And sorry, so now if you put it along scribe plus, what's going to happen to your? I guess you're still doing the Euclidean path integral. So what's happening to the corresponding branch cuts?
Yeah, we really have to start it in Euclidean and then analytically continue up to scribe plus.
So you still have the same Euclidean picture, except that now you just have flat space instead of gluing previous.
That's right. Yeah.
Okay. Thanks.
Although in that case, we do not have global wormhole solutions. I think that's just a technical issue, but we don't have them. So we use this along scribe plus. I think what Suvrat would say is that the algebra of observables on scribe plus doesn't factorize in such a way that you can really talk about SR. So I think he would say that we don't know that what we're calculating is really well defined on scribe plus, and I think that's a valid objection, that we don't really understand how to split regions on scribe plus in quantum gravity. We're just assuming that we can do it. In terms of the actual calculation that's done, this has to do with assuming that you're allowed to put this defect. You have to put a defect here to calculate this entanglement entropy, and we assume that we're allowed to do that. But I think that one could object.
One could object because.
Because the Hilbert space doesn't really split. I mean,
so
it's
a problem with
like
defining what SR is, right?
What?
That's a problem with defining what SR is, because,
yeah, it's a little like the discussion of entanglement and gauge theory, where you can use the replica trick to calculate something, but the Hilbert space doesn't really split in gauge theory because of the Gauss constraint. So then you have to ask, well, what did I really just calculate? You calculated something by the replica trick, but was it really the entropy of something? What did you really just calculate? And I think in gauge theory, there's been a lot of progress in understanding that in the last few years, but in gravity, it's still.
But here you're at asymptotic infinity, so one might hope that in the asymptotic space-time, maybe gravity is weak enough to, well.
On the one hand, you would hope that, but on the other hand, well, here's the sort of echoing Subrat's paper here, but the Hamiltonian is a boundary term at spatial infinity. And therefore, the Hamiltonian lives in the algebra of region R. And then you could argue that, well, if you have the Hamiltonian, then you can evolve region R and just cover all of Scri plus. So it doesn't really make sense to talk about the subalgebra of observables on region R. So on the one hand, gravity is weak.
Oh.
Sorry, I can't hear Tom anymore. Can anybody else?
I don't either. I think his connection broke down.
Yeah, his picture seems to be frozen.
Yeah, I think the image froze. Probably the best.
He's disappeared to an island, I think. But his entanglement lives on.
Can we get, does anybody know how to contact him by phone or something?
No.
Connect and connect again.
What will happen is he will try to connect again.
Yep, no, he vanished. Yeah, that's good.
We hope that he does anyway. General question in this context of Zooming: is it good etiquette to actually to show your video when you ask a question? I think it should be. You can't just stand back and be blanked out and ask a question.
Officially, this is illegal.
So, wait.
In what country?
In Europe.
What is illegal?
Okay, Tom is back here.
Oh, good, Tom.
He needs to unmute.
Yeah. Okay.
Sorry, I don't know if that was me or what happened.
Joseph probably just chucked you out. Don't worry.
Oh, you know.
I thought maybe my microwave was on, which kicks me off the internet. So that's where I ran.
Oh, interesting. Interesting. We didn't see you running. We just saw your image freezing, and then you just came back. So your image froze before you run.
Oh, okay.
Pancake rather?
What?
Did his image freeze or just pancake?
No, just froze.
Okay.
Okay, so more questions there?
Yeah, I guess I have one. So I'm still a little bit puzzled about the status of this quantum contribution to the generalized entropy. So I can consider a one-parameter family of states which have the same amount of bulk radiation, but I just declare that some percentage X of the bulk radiation are Hawking quanta that came out of the black hole, and some other fraction, 1 minus X, are just, bulk gravitons. And it seems like as you dial X between 0 and 1, you at some point are claiming that the saddle point in the geometry is changing. But a bulk observer would just say, oh, I have, n gravitons in the state. So somehow there's some private knowledge about the microscopics that's invisible to a low energy observer that is somehow having some kind of macroscopic effect on the low energy effective theory. Could you comment on that?
Yeah, I agree this is mysterious. I think what the Euclidean path integral is telling us is that, or what this formula, the island formula, is telling us is that to calculate the entropy of a system coupled to gravity, it knows how the state was formed. right? You have to do this Euclidean path integral that starts at early times and evolves to late times. And that knows about the black hole interior. It knows about the details of this state, and it knows that it knows that those pairs are entangled with the interior, not just some actual thermal gas. As for whether this is accessible to a low energy observer, I think well, this sort of connects to the question of those e to the minus of the e to the plus s times e to the minus s. The low energy observer only knows the density matrix up to some corrections, and presumably does not know how to measure the non-perturbative contributions to the off-diagonal matrix elements. So that observer isn't really going to see a contradiction between the fact that all the low point, well, just between the fact that they seem to be in this thermal state and yet don't have thermal entropy. They're not going to see a contradiction because they're going to keep track of that e to the minus s error and realize that they don't know the entropy. Maybe part of what you're getting at is that this formula, the island formula, is supposed to be a, let's go, I'm not sharing screen anymore. Well, the island formula is supposed to be a formula for the von Neumann entropy of region R, like the true von Neumann entropy of region R. But in that formula, there's the second term is what I call the semi-classical entropy. And you're supposed to calculate that second term in quantum field theory on the black hole background. So it sort of involves a potentially wrong term in the calculation of what's supposed to be the right term, which is strange, but that's what the formula is.
So that calculation, again, I sound like a broken record, is done in the Euclidean black hole background or the Lorentzian black hole background?
Which calculation?
The one you just stated, that you're supposed to calculate that second term in a semi-classical way in a quantum field theory in a black hole background.
Actually, the second term you can calculate either way. You'll get the same answer. The first term, the gravitational contribution, the reason you have to calculate that in Euclidean is because, well, we don't have any Lorentzian way of calculating black hole entropy. So
right.
Low energies.
I don't know if there are more questions. We're already half an hour over the time. So thanks a lot for the seminar, and let's thank Tom again.
Thank you. Yay.
Thank you.
Thanks, everyone.
Very nice.
Bye, guys.
Bye.
Bye.
And thanks a lot.
Bye.